You like understood
Very smart move.
PRPP, bro.
I'll take him on like
The hard one.
a hard day for the last weekend.
Okay.
Does your computer have audio?
I don't think so. You just, I'm just gonna have to yell.
Yeah. Nice, good stuff.
You know what that is?
What? What's that?
The bad one.
It's a bad song?
Yes.
Is it by Notorious Small?
Oh. I forgot that. I was like, so fun. Since
Hmm.
you're just playing. It's small.
Okay. So today we have a very special presentation called Methods for Evaluating Integrals by Kevin A. Before we get started, how's everyone doing?
You can always be there. I can always be fully caught up to the home.
Are you?
Yeah. No.
How close are you?
Making more.
For homework? For homework with no work or for homeworks with just not completed?
Oh, no. I said more less. With nothing.
With nothing. So 4 with nothing. So fingers for how many with nothing? 2 with nothing?
Wait, what?
How not problems, homework weeks.
Oh,
They got absolutely nothing.
oh, no.
Are we supposed to be?
Okay. So currently you should have finished up to 616, which would be homework 7.
Mission.
That would be at the end of last week. Is that 3? 3 to 4? Okay. Okay. So at some point we should ask the question when we want to move up this catch up in debugging. Now, usually I try to get through all of integration because it's just basically 3 presentations. How is it going with your code? Your final project? What was your requirement from Monday's class?
The import.
Yeah. And you have that?
Yeah. What are you about proposing?
So whatever you propose to do, you're going to summarize it in what we call words. Now, this is very different from code. So we're going to describe to me, the reader, what you plan to do. And that way I can see you making some form of progress on this problem. If you start with something like a homework problem and you are working on advancing that, feel free to copy and paste that homework problem in, right? Say, here's the code that I plan on using, and here's how I plan to adapt it using this really helpful thing for me, words. Okay? Okay. Any last questions before we let Kevin take it away? What do you mean? I'm just going to look at it and make sure that you are actually doing it. Because the thing is it's just a communication, right? Like, I just want to know that you're working. I have no problem failing all of them, right? Like, that'll make me sad inside my heart, but it won't do anything to my job, right? So what would I prefer to do? I don't think a professor who fails every one of his students is good, but I also can't do the work for you. Right? So all I can do is continually remind you, continually bug you. And at the end of the day, right? You know this saying, go bring a horse to water. What's the end of it?
Can't make them drink.
Can't make him drink. Right? You are the horse. Class is the water. Okay. Water good for you. Water good for thirsty horse. Thirsty horse has to decide to drink. Okay. Okay, cash dollars. Kevin, at your leisure.
All right. So today we're going to start out doing his favorite thing, taking integrals. So going against everything Chris Monty stands for, we will start with the simple ones of one variable over a finite range. So to begin, we're going to learn the trapezoidal rule. So you see here, we have a function of x and we calculate its integral with respect to x from a to b.
Okay, let me pause you for a second here. You even went a little too deep. What would I do in this circumstance? What's the first question I would ask? Before that, what's an integral?
Area under the curve.
No, you know that. You would ask the class.
So if the class should know that.
Right? Class should know this. Area under the curve. Right? Okay.
Okay. So that was my next sentence, literally. This is done by taking the area under the curve.
Okay, all right. Well, then you can. So the thing is if you know you're about to say that, one thing that's really good, especially for science communication, instead of just yap, 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 make it a conversation, right? And thinking about now your final presentation, feel free, like you don't have to sit down. I mean, you can, of course, do this if you want, like practice and memorize exactly what you're going to say. But the more that you can engage the audience, because these are your peers, right? Ask them questions. Trinity, what's the area under the curve? Now, she might be mad at you for doing that, but when she gets it right, you'll look really great, right? Okay.
So as you see, this is figure 5.1. We see a line and we try to accurately obtain this area. And the way that they do it initially is with squares, right? But you cannot get like very accurate. So how could we make this very accurate, more accurate? They, instead of using squares, they start using these trapezoids looking things, right? And you can see that that's more accurate in figure B. It's more accurate than figure A. So how do we make this even more accurate, right? You notice that A and B are both cut into 4 segments. The way you would make this more accurate is essentially getting more segments. Give me 1 second.
So this is really good so far. The only clarification I'm going to make is that he said the word square, but I think what he meant was everyone else. Yeah, no worries. You could even have presented that like as a trick, right? Bag secured. Okay, good.
Is today presentation day?
No, every day is presentation day. Computational, remember?
Can I chill in here?
Yeah, you're welcome to. Make sure you take notes on Kevin's presentation.
No, please. No.
Okay, go ahead.
Now I'm nervous. So oh my God. The area under one segment, right? If we take the area under one segment, we can just add the summation of all of these segments and that'll give you the total area under the curve, right? And we want to get a more accurate like answer to the area. So we essentially add more segments, but it starts, once you start adding like very large segments, it'll start to get really slow. Like your code will start looking really slow. So here we look at where is it? Example 5.1, and I took the liberty of writing the code here. See, we make a use defined function of our curve, and then they have 10 segments from 0 to B, right? And then we run it, and then we get this. This is our area, right? But it's not as accurate as it could be. So when they start introducing, see, it says that this is great, it works, but it's not entirely accurate. So we can start by increasing the number of segments. So instead of n equals 10, I went to 1,000, and it took a little longer, but I got a better accurate answer, right?
Can we pause you for a second? Can we go back up just to show me the 10 one? So does anyone want to help us just discern what's going on in this code? 'Cause you-
Is how many steps?
Good. Yeah. So this is the number of slices, right? You've heard that TikTok thing? That's enough slices, right?
Yeah.
This is what we're doing to the pie. We have some area under a curve and we start cutting it up. First, we cut it in half. Then we cut those halves into halves. And as you keep slicing it up, right, you make these circular objects really, really thin, such that if you laid them all out side by side, you would make something that approximated a rectangle, right? And you put one on the other like that. Okay, so what does this section do here? Yeah. No, go for it, Emmanuel.
Start, stop, step size.
Good. Start, stop, step size. So this is something that we imported from our understanding of the previous one, right? All right, Trinity, what's this?
That's our solution.
No.
Is that not the rectangle selection? We do have.
Is it the whole thing?
Is that the whole thing?
Is it the whole thing? No. It's something about the summation, but it's not the summation.
It's the points that you're taking from F of A to.
Anyone? So this is really important because it's not going to be quite obvious, okay? Okay. This is B, this is A, this is F of A, this is F of B. Okay. Let's do the boxes inside. And I'm going to be even simpler. I'm going to do rectangles. Okay. Rectangle, 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 so on and so forth into the last rectangle, right? Okay. Let's count them. They all have width what?
B minus A.
They all have H. That's what I would say. Right? So let's call this H. Okay. So length times width is H times. Yeah, F of A, for example, right? Now, if I'm a little smarter and I do a trapezoid like this, then what do I do? This is H. And what's the, how do I do a trapezoid? How do I make a trapezoid in math class? Do you remember that? Area of a trapezoid?
1/2 times H times the F of A plus F of B.
Right. Good. Okay. So this is A and this is B in that context. But let's be a little bit more clever here. Okay, we'll realize that we have more than just A and B. We're not going to do one giant trapezoid. Let's call this one AA. Okay. You see that? Now, what about its neighbor? The neighbor that starts at AA and goes to AB. How big is that in area?
It's AA plus AB.
Good. So it's 1/2 H FAA plus FAB. Are you seeing a pattern yet? What's the pattern? Yeah, so it's multiplied by A, right? Here, this one is shared between two of them. So how many times does it show up if I add all of these boxes together? How many times does FAA show up?
FA shows up twice.
Shows up twice. Because you count it once for the right side of box 1, and you count it once for the left side of box 2. Now, if it was a box 3, you would do that again with FAB. But what about the beginning, A, and the end, B?
They show up once.
They show up once. So have a look at the sum. This one is 1/2 times FA plus FB. This is the end points. And on the inside, notice we don't multiply by half. Why is that? Bingo, bingo. You have 1/2 and it shows up twice, so therefore it cancels. Okay? So when we do an integral like this, a sum like this, first we set up the sum by taking the end points. And then we do the interior. That's the only thing that I wanted to point out here. So if you're going to write this down, if you're going to code it, just write endpoints and then interior sum. Okay.
So. Okay, so that was with n equals 10, then we did it with n equals 1,000, but as I said before, it's more accurate, but it does take longer.
How much longer? Can you do the time there? Just show me the difference. Oh, wow. So like 9 times longer.
Yeah. So 101, 109, but also like 8. I mean, we could crank it up, we'll do it 10,000.
No, but I mean, think about that, right? Just imagining going from 0.01 to 0.09 is a factor 9. Okay, and how much better did you get in accuracy?
Oh, it went to so this is 2% accurate.
Yep.
I'm sorry, it's off by about 2% is what I should say.
Yeah.
This is about off by 2%. This is off by 0.0002%.
Good. So you got really, really good for a factor of 10 runtime. Okay.
Okay, so that is the trapezoidal rule, but there's a different method which is called Simpson's rule.
Not Homer's rule. That's funny.
I know. I was trying to be funny, but
I liked it. I just said it was funny.
no, I know, but
No one else laughed. You gotta say the joke. That's good.
so as we saw, the trapezoidal rule is good for not so accurate calculations, but when we want better measurements, we use the Simpson's rule. So as I said, when we increase n, it could take a lot longer time. So we created Simpson's rule, not we, but like physicists created Simpson's rule to not have it be so long.
Good.
So while the trapezoidal rule approximates the curve using straight line segments, this is not always best when trying to find the area under the curve. So Simpson's rule created this. As you can see here, it'll take this segment and it'll divide it in 2. So it's not a straight line, I guess we could say. So they take a pair of 2 adjacent slices and they fit a quadratic through 3 points now instead of 2. We start the function with spacing points as h. The 3 points are written as -h, 0, and h. So an example of this would be the Pythagorean theorem, where f of -h is h squared minus bh plus c, where f of 0 is c, f of h is this equation right here. And then when we solve for this, we would.
So that's hold on. Just go for folks who are following along. It's f of 0, and this is f of h, right? And so this point in the middle, even though we cut it up in our mind, this is still h. Right?
Well, f of 0 is in the middle.
Oh.
Yeah,
And this is f of h.
that's f of h and the one. And
Is this
for-
h?
that,
This
in
is
the
minus
beginning
h.
is minus h. Yeah.
Minus h, okay.
Yeah,
Minus h, 0, h.
yeah. And so when you solve for that, you get this equation, 5.7. So, if we know that the final area involves only h, and the value of the function at evenly spaced points, this is, I'm sorry, I'm really not good at
That's okay.
presenting. I can show you better with an example.
Yeah, the example's easier.
So if we look at this, this is example 5.1 that we just showed. And then I changed it with now new, you have our user defined function, which is the same curve, same A to B and same set. But now we made it so that what's it called? That instead of just it being one straight line segment, now there's two segments, and it still is the same summation, except the 1/2 is not here. I forgot why I did.
Okay, scroll down a little bit on the right-hand side.
On the right hand side.
Yep. Okay. So let's write the integral here. Okay, wait, scroll up. Yeah. Right? So this is how we approximate the integral. 1/3 h fa, and then they kind of like summarize it here, and they do 1/3 h fa plus fb, and then they have two sums. Okay, and this sum here is for when k, which is wherever you are in the iteration, is odd compared to when it's even. And you'll notice here in the summation, it starts at 1 for odd, obviously. And for this one, for the even, it starts at 2. And one thing that is happening right away is you see these funny numbers. 4, 2, 1/3. You're like, what the fuck is that? Right? So one thing that I want to point out here is here we took the average of these 2 points in order to find an average height to approximate the box size. You're doing something similar, but it's called a weighted average. What this does is it assigns weights, particular importance to various points along your number line. So if you're going between points A and B, not every point in there is uniformly useful. In fact, you saw in the trapezoidal rule, which 2 points are the least important? This is a question. In trapezoidal, which 2 points are the least important to your integral?
Endpoints.
What?
Endpoints.
The endpoints. Why?
Because they only occur once.
Because they're worth 1/2. Right? You're saying the same thing, but the way that we think about them is the weight. Right? They retain that initial weight of 1/2, where everyone else is double counted and therefore has a higher weight, a weight of 1. Right? So in this particular circumstance, if I multiply this 1/3 in, okay, boom, boom, then these become 1/3 each. This is 4/3, and this is 2/3. So who's the most important point in your trapezoidal Simpsons rule?
The odd.
The odd points. Okay, who's next?
The even points.
Even points. And finally, the endpoints are still the losers, right? So what you're doing here, and we will do this for even higher and higher dimensions. So basically, what Kevin's talking about here is we started with the simplest approximation, box, okay? That's kind of a dumb approximation. So we're like, oh, we're physicists. Let's use slope, rise over run. And then after slope, we said, let's use curve, okay? You'll notice that in each of those circumstances, I changed the polynomial number. The first one, box, is a constant. The second one is a line. The third one is a parabola. What's the next line? A cubic function, right? And that is really nice. It has this nice curvature. So in fact, we will talk about the mathematics necessary to convert the area under a curve using a cubic, right? And you can keep going and keep going and keep going. Now, at some point, you're you're just doing like a 90-point derivation of the area under the curve, and so it's not as helpful. So there's a trade-off there. But to go back to your code here, you want to walk through it? Do you feel confident in talking about this part?
Well, right here is our summations, right? So this right here is the odd. I don't feel confident as confident.
Yeah.
Looking at it right now.
So I'm not sure I would write it this way. And we're going to be able to write it together as a family. Okay. I would write it in a way that looks gross. This looks sleek. You know, there's something like really nice about having something with an if statement in line. Right? This is second year programming in graduate school. Okay. So I would be dumb. Because when I'm dumb, at least I can see where in the line my mistake is. So I would do three things here. Just like I did for the trapezoidal rule, I would start by first taking the sum, and I would initialize the sum at the endpoints. I would do 1/3 of this plus this. Right? And then I would take two different sums and I would add them. So I would say, if you're even, do this. If you're odd, do this. Right? And you just work through 1, 2, 1, 2, 1, 2, 1, 2, which is essentially what's being said here, right? This isn't a statement about even or odd, right? But I would put it into a chain so you could watch it all happen, right? That makes sense? Yeah.
Mentioned Simpson's rule, and then it mentioned extended Simpson's rule. What's the difference in using between the two?
I mean, that's called the extended Simpsons rule. It's the same.
This right here is used.
Yeah, the one that we're using, the one that we should use is this one here, which is the extended Simpsons. Okay. So yeah, this one too. This is a nice little warning, right? So let's say you accidentally use 101 slices. Simpson's rule won't converge because the last slice won't be matched up with the endpoint. So you can just have it do, this is fun. This is also an advanced technique. This is called a raise error. This will essentially, you know how you get that red stuff when your code is doing bad stuff?
Yeah, here.
They're called raise errors. And you can get it to say whatever you want. You can say, Prismani has very few hairs on his head, right? And that could be a raise error. Or it could be like, you forgot to add water to your soup this morning, right? Whatever your raise error wants to be. Okay. And then at the very end, you have this 1/3 times s. That's the same thing that we did before, but instead of tacking on, right? Like before we were doing just h times the thing at the very end. Now we do 1/3 h, and that applies to all of them. So it's okay here that his sum did not start with the 1/3.
Yeah.
Because it's coming along here. And if you want to be even prettier, right? You don't have to do I Simpson. This is perfectly fine. What could you do for this last line?
Extended Simpson, I don't know. Extended Simpson rule or.
So if you want to keep in, sort of the technique and like typewriting that you're doing with your code, I would do S times equals H/3. Right? Because we can still use times equal. So this is a plus equal, then you have a times equal. Boom. Now you just print S. C'est bon? Okay. So interestingly enough, this is going to feel like a lot of the work you've done before. You're going to be able, oh, by the way, thanks, Kevin. Round of applause. Yeah. Okay. So this is going to feel like a lot of the work you've done before. Okay. It's going to feel a little bit different. You're not going to have the physical intuition. So when we get to that part of the code, you won't say, oh, this feels like pi/2. You'll say, hey, I computed this either algebraically or I popped it into Wolfram and I was able to show that this worked or not. And the reason why we're doing this particular is we are going back to this idea where we're thinking about how approximations lead to error in our code and how we can mitigate those approximation errors by, say, making our slices thinner or by making a better approximation to the curve we're going to naturally reduce how off our answer is, right? Questions, comments, concerns? And Alyssa on Wednesday is going to tell you about all those errors and how you, for you, can choose the right step. That's not about shoes. Okay, so everyone find your friend that you want to work with. I'm gonna kick you out unless you want to show your. Okay. Is anyone online? Okay, I'm gonna close this out then.